Hi everyone, I'm going to rely heavily on the calculator here to help us through our video solutions for today. We're going to start with number 7 on page 263. First thing I'm going to do is I'm going to define matrix P to be the matrix that we're given in number 7. That's 0.7, 0.1, 0.1, 0.2, 0.8, 0.2, 0.1, 0.1, and 0.7. And then, as we know, we're trying to solve the equation Px equals x. I'm just typing that in there. We're not going to do anything with that. The way to solve that is to take P minus the 3 by 3 identity. It gives us a new matrix, and we're going to solve that matrix times x equals 0. So what I'm going to do is I'm going to augment that matrix with the 0 vector. Okay, we now have a new matrix with the 0 vector augmented, and I'm going to reref that, getting me this. I'm going to pull that over to my other screen so that I can kind of dissect that and we can talk about what that means. Okay, so for number 7, this means that x3 is free, right? So we can say that x1 is equal to x3, x2 is equal to 2x3, and x3 is x3. But we still have the condition that x1 plus x2 plus x3 must equal 1, or 4, sorry, my mistake, that should be a 3, or 4x3 equals 1, so x3 equals 1/4. If that's the case, then our steady state vector should be the vector 1/4, 1/2, 1/4. If we're letting x3 be 1/4, I'm just going to check that with my solution guide real quick. And that is right. 1/4, 1/2, 1/4. That's the steady state. Okay, going on to 16. In Detroit, Hertz Rent-A-Car has a fleet of about 2,000 cars. The pattern of rental and return locations is given by the fractions in the table below. On a typical day, about how many cars will be rented or ready to rent from the downtown location. That problem is essentially asking for the steady state vector once again. So we're going to kind of go through this process one more time and see what happens. I'm going to enter in fractions this time, just to be safe with my computations at the end, okay? So I'm going to define the matrix P to be our 2 by 2. I'm going to call it 9/10, 1/100, 9/100, 1/100, 9/10, 1/100, oops, 9/100, 9/100. Okay, I think this is going to help us with our rereffing. All right, so I'm going to augment that matrix with the 0 vector. I may have never shown you this command, did I? Augment with the 0 vector. It's kind of a cool command that'll make a new matrix with that thing augmented on the end. I'm going to reref the result. That gets me this. Okay, wait, that's not what I'm expecting. Hang on, what did I do wrong? Okay. Enter everything in right. 9/10. I know what I did. That's a dumb move. Okay, what did I forget to do? I hope you can figure that out. I forgot to do P minus the identity. Do P minus the identity. Then I can augment that thing with the 0 vector. Great. Now we're augmented with the 0 vector. Now we can reref. There we go. That's much better. Okay, so I'm going to pull that over to my other screen, and you'll be able to see what's going on. Okay, so this is number 16, and what we have is that x1 equals 91/99 x3, x2 equals 19/99 x3, and x3 equals x3. So once again, this means that the sum of these things has to equal 1. So let's take 91/99 plus 19/99 plus 1. 19/9 x3 equals 1. So x3 equals 9/19. Okay, if that is the case, let me confirm that real quick. 9/19 is that decimal, which is good. Okay, so this means that our first element in our steady state is going to be 91 over 99 times 9/19. 9/19, which gets us 91 over 209. And that is correct. 1 over 209. The second element is going to be 9/99ths, right? Or 1/11th. And the third element is going to be 9/19ths. So that's our steady state. And don't make the mistake I did. Make sure that you first subtract the identity before augmenting with zeros and rereffing. All right, that's the 2 from 4/9. When I do the 2 from 5/1, and I know I just barely touched on 5/1 in class, but we should be able to answer these questions quickly with the calculator. So number 3 says, is 1, 4 an eigenvector of -3, 1, -3, 8? If so, find the eigenvalue. Well, something is an eigenvector when it gets multiplied by the matrix, and the result is simply a scalar of the original vector. So that's what we're going to test. Is -3, 1, -3, 8 times 1, 4 just a scalar of 1, 4? And the answer is no. See, 129. 129 is not a scalar of 1, 4. So for number 3, our answer is no, because the matrix times the vector does not equal just a scalar times that vector. So that one is no. Let's take a look at 5. So we're going to take the matrix 3, 3, 7, 9, -4, -5, 1, 2, 4, 4, and we're going to multiply it by the vector 4, -3, 1. Okay, cool. So that thing is a scalar multiple of the original vector, isn't it? Right? 0, 0, 0 is a scalar multiple of 4, -3, 1, which means that, yes, it's an eigenvalue, and AV equals 0 times V. So the corresponding eigenvalue equals 0. And of course, we'll talk a lot more about that in class.